All right. So today we're going to be analyzing or introduce trig functions. Trigonometric functions. And in order for us to understand trig functions, there we go. Let me just make sure this is focused. In order for us to do a good understanding of trig functions, we must have our angles down. So today we're going to be looking at a review of angles and circles. Okay. So the very first thing I'm going to talk to you about is this beautiful thing called the unit circle. And just the composition of an angle. So we recognized if I take a coordinate plane, here's my coordinate plane, and what I'm going to do is I'm going to draw an angle on here, and it has a center or its vertex at the origin. So here is one ray of my angle, and I'm going to do another ray right here. Okay. So the basic definition of an angle is two rays that are joined at one point. This point is called the vertex. And what we're looking at is truly this little space right here that it creates. This is my angle, and it's represented by theta. So we recognize that my angle variable is this guy right here. This is called theta. Okay. And so you'll notice that I will always put a theta here. Okay. And let's talk about what this angle is. This angle is in standard position. So if I'm looking at a definition of standard position, so an angle is in standard position if the vertex is at the origin. So is my vertex at the origin? Right there. Yes, it is. And also, it has an initial ray on x-axis. Okay, and it has to be the positive x-axis. So this right here, this guy right here, that's called the initial ray. Let me do them in orange. That way it's a little bit more distinct. So this initial ray right here is laying on the x-axis. So that's called the initial ray. And this ray right here is called the terminal ray. Okay. So that's when an angle is in standard position, is if it has its vertex on the origin and the initial ray is lying on the positive x-axis. Okay. And notice I'm going to indicate, there's arrows. Do you see this arrow that I drew here? That's really important because this arrow is giving direction to my angle. So if my angle opens up in a counterclockwise, so theta is positive if the angle opens up counterclockwise. I don't know how to spell today. Counterclockwise. Okay, so if it opens up in that direction, it's positive. If my angle, so theta is negative if angle opens in clockwise position. So remember, clockwise means this way. So theta, if it opens this way, then theta is negative. So this is positive, this way is negative. Okay, so remember, that's my initial one. If it opens this way, it's negative. And then here, there's my initial, put it here. There's my initial ray. If it opens up this way, it's positive. Okay, so that's really important to understand. Another basic symbol. Another basic symbol is a right angle. You will always know it's a right angle by that little puppy right there, which means that this right here creates a perfect bisection, which is now this theta is equal to 90 degrees. Okay, so something we can know. Another little crash course on angles is called coterminal angles. That's my symbol for angles. And let's talk about what coterminal angles are. These are angles that share the same initial rate and terminal rate, but the direction of analysis they're equivalent, but they have different values. So I'm going to draw another little coordinate plane. And I'm going to draw a 45-degree angle. Okay, so we're going to use intuition to do this. Okay, vertex is 0 because all my angles for this intro are always going to be in standard position. So here's my first angle. There's my initial ray. I recognize that straight up. So notice this one was completely horizontal and this one was completely vertical, and that gave me 90. But I want to draw 45. Recognize that half of 90 is 45, so I'm literally going to just bisect that area exactly at the halfway point. So now I've drawn a 45-degree angle. Okay? I'm going to analyze this two different ways. The very first way is up this, which gives me that my theta is 45 degrees. Okay, so let's go back and make sure that we recognize that every quadrant measures 90 degrees. So remember how I said this is 90 degrees? So this is 90 degrees. This right here is 90 degrees. This right here is 90 degrees. And this right here is 90 degrees. So if I want to look at a straight angle is 90 plus 90, which means that a straight angle is 180. And if I want to go an entire rotation, that means I go 90 plus 90 plus 90 plus 90, which gives me 360. Okay? So if I was to go all the way around, that's 360. But if I look at this through the aspect of to a different color, I will do, I'll do blue. What would be this angle here, like this? Notice I'm still using the same rays. It's now my direction change. So that angle there, if I go 360 and I subtract the 45, that gives me a difference of 315. But now notice that I traveled in a clockwise position. So now this angle that I traveled is now negative 315 degrees. However, they are coterminal, so they are sharing the same rays. It's just the analysis of the direction that I'm taking it on. And there's also, what happens if I was to say, well, what if I was to do multiple rotations? So now that means that I have one rotation this way and then a little bit more. So that means, if you notice, my orange went 360 degrees plus another 45. And so that theta is going to be 360 degrees. Oops. 360 degrees plus 45 gives me 405 degrees. Each one of these angles are coterminal angles because they all share the same initial and terminating ray. However, it's now the analysis of the direction that are going to make that distinguish them. So that's another crash course on coterminal angles. Now let's go ahead and talk about the way that we measure theta. Theta is so important because theta gives us a lot of valuable insights. Yeah. Okay. Let's talk about theta. Okay. Theta can have two ways of being measured. We will start with degrees. However, once we progress to a study of calculus, these degrees are going to be turned into radians. So it is to your best benefit to make sure that you recognize how you convert degrees to radians and radians to degrees, which I'm going to show you today. But also I'm going to give you the starting. Today's lecture gets you started into understanding the unit circle, and the unit circle is what you need to memorize so that you have an easier experience with trig functions and analyzing them through calculus and on. Okay? So the unit of measure for angles there's two. There's degrees, and then there's radians. Okay? So today I'm going to show you how you can use both of these, and you can convert from both of them, and then you're going to be able to visualize the angle. Okay? So we're going to start with degrees. We kind of already started with that. And we recognize let's go with degrees real quick. Again, we recognize, I'm going to do a couple of graphs to showcase degrees. We recognize that degrees is something we already know. This is 90 degrees. We recognize that this like this, so I'll put it up like that. This here is 180 degrees. If I go like this, right there like that, this is 90 plus 90 plus 90 gives me 270 degrees, right? And now notice that if my initial ray and my terminating ray land on the same thing, that gives me this little circle thing. This is going to give me 360 degrees. And then I can also do smaller degrees. Like here, I can do maybe like, this is an approximation that's like 20 degrees. Cool? So just a little visual of like how we know degrees. We recognize 90 degrees. This is from like geometry. Now let's talk radians real quick. Okay, what is a radian? Okay, so in order for me to discuss radians, I got to talk about circles. And I'm going to talk about this little picture here. Did you notice that when I went 360 degrees, I made like a little perfect circle here? And so that's why it's so important to analyze this using the unit circle. And the unit circle is just a circle that we use, but this unit circle has a couple of properties that are uniform. The first thing is that its center is at 0, 0. And it has a radius of 1. Okay, so watch what I'm going to do. I'm just going to draw it out. Okay, and I'm going to say, draw that out in pink. So the unit circle has a center at 0, 0, and it has a radius of 1. So for the sake of this, my radius, that's going to be 1, 0, 3, 4, 5, right there, 0, 1, negative 1, 0, and 0, negative 1. Because as I draw my unit circle, it's a sketch. This is my unit circle. Notice my radius, r equals 1 at any given point. Any one of these rays, these are radius to a circle, will all, oh, that's going to give me 1. Okay? So let's talk about this, and we're going to talk about arc sine too. So arc length, sorry. Let's talk about arc length. Arc length, remember today's a crash course. Arc length is this puppy right here. Arc length is this little distance. So, like, let's say I just want to analyze from here to here on this unit circle. The arc length that I'm interested in is this little, it's like, if I see this little pizza slice here, my arc length is just this crust length, okay? That's what arc length is. So arc length is this guy right here. And I want to recognize that the arc length formula is S is equal to R theta. Okay, that's the formula for arc length. And the theta must be in radians. Arc length, it does not use degrees. So just a little crash course. So let's talk about why I'm using arc length, because I'm going to show you how we already know arc length. I'm going to redraw that unit circle. Okay, so I'm going to redraw that unit circle. Okay, there's my unit circle. Okay. And what happens if I want to know the entire arc length of this circle? Like, I want to know how much does all this crust measure? Like, what's the distance of the entire crust of this pizza? Don't we already know that? Remember? That's called circumference, right? So circumference has a formula, and the formula is called C equals 2 pi r, which means radius. Remember, this is my unit circle though, right? So the unit circle has a radius of 1. So I recognize that the circumference of this pizza here is going to be 2 pi. So this circumference here, because remember, r equals 1, is 2 pi. Okay? Just want to make sure we recognize that. So the arc length of the entire circle is called circumference. Okay? Now let's talk about why is it that I'm bringing all these prior concepts into it. Because when I look at a radian here is a unit of measure to angles, okay? And it measures this. So 1 radian is equivalent to the arc length here. Like if this is my R and this is my R, 1 radian is this angle opening that creates arc length, that little crust of that pizza that's equivalent to this radius, okay? So that means that from here to here must also be R for that to be 1 radian, okay? So let's talk about this. Why is it that I'm looking at the entire circumference to recognize what a radian is? We recognize that the entire circumference of a circle, of the unit circle, because it has a radius of 1, is 2 pi r. Well, r is 1, so it becomes 2 pi. Now remember that I said, remember that formula I talked about, which was called arc length? And arc length had S equals R theta, but theta must be in radians. Okay. So if I want to just take this here, like I just want to figure out, like in this slice here, what is this length here? I would use this formula, which would take theta in radians multiplied by my radius, and it would give me that measure of that distance of that crust. So that's what arc length is. But I want to use the formula for arc length so I can show you that I'm able to derive radian measure. So I want to know what is the arc length of the entire circle, right? So that's going to be my question. What is the arc length of the entire circle? We recognized earlier that the arc length of the entire circle was right here. It was the circumference because I'm looking at the entire crust of the entire pizza, which is my definition for circumference. So I'm going to put these two together and we're going to prove something and derive it. So I'm going to start with my arc length formula. I recognize that my radius is 1 because I'm looking at a circle. And I want to know what the entire arc length of the circle is, which I know is 2 pi. So what I already know so far is that I'm using the unit circle for my radius is 1. I also know that the entire circle means that my arc length is 2 pi. Yes? So now I'm going to place that into my formula so I can derive my theta. So what I'm trying to do is by using the entire circle and plugging in two things that I already know, I'm able to then derive and prove how many radians are there in one entire revolution around this circle. That's my objective here. So I recognize that my arc length of the entire circle is 2 pi. So instead of writing s, I'm going to write 2 pi. I know that my radius is 1. And I don't know what theta is, but I know that theta is in radians. So let's go ahead and see what this gives me. Theta times r gives me 2 pi gives me theta. So I recognize that my theta is 2 pi when I'm looking at the arc length of the entire circle, which means that one entire revolution this is my initial ray, one entire revolution, and my terminal ray is right there as well. One entire revolution is equivalent to 2 pi radians. Because remember, theta is in radians. So I hope you recognize that I use this to prove that one entire revolution is 2 pi radians. Okay? Let's go ahead and now look at what I mean by this. This is how you got to learn how to do the analysis through a lens of degrees and a lens of radians. And you must be fluent in radian analysis so you be successful in trig. So I'm going to show now a comparison of radians and degrees. First thing you need to know is you need to understand how to compare them, and you also need to understand how to convert from and to them. Okay? Let me just make sure my paper's straight. There we go. Okay? So I'm going to draw a couple of circles here, unit circles. Recognize that these are all unit circles with center at 0, 0, and these are just sketches. And my radius is 1. So I want to verify what is, there's my initial ray. It goes all around. So if I'm looking at degrees, let me just make sure that there we go. And this is radius. If I'm looking at degrees, one entire revolution is 360 degrees. And by what we just proved earlier, one entire revolution of radians is 2 radians. Cool. What happens if I'm just looking now? Okay, well, there's my initial ray. What happens when I'm just looking here to here? So here, the entire revolution gave me theta equals 360 or theta equals 2 pi rads. So you can write it like that, 2 pi rad. And that's a revolution that occurred one entire circle, one entire revolution, yeah? Now, actually, let me use a highlighter for that. So, one entire revolution. There we go. Now look at this one. Here's my, remember, right here. How much is that in comparison to one entire revolution? Now I'm just looking at technically half a revolution, yes? So if I'm only looking at half a revolution, how much is that in degrees? It's a straight angle. Notice it's a straight angle. So straight angle is 180 degrees. What's half of 360? Should be 180 degrees. So let's see. Let's prove it with my little calculator here. So I have 360. Oops. I want to know what's half of 360. 180. Look at that beauty right there. So now let's look if we can use that same logic to say, I know that 360 degrees is 2 pi radians. I know that half of 360 degrees is 180. So what's going to be the equivalency over here? Well, if these are equal like this, and I went this way to half, wouldn't 2 pi, half of 2 pi radians be pi radians? So again, 1/2 revolution on my unit circle means that my theta is equal to 180 degrees, or this means theta is now equal just to 1 pi rad. Okay? Now let's see if I can take this a little bit further. What happens if I use my terminal ray? Here, here's my starting ray, and this time I only go here to here. So now, how much of a revolution am I making? Right here from here. So this was 1 whole revolution. This was half a revolution, and now this is 1/4 of a revolution. So let me just go ahead and label that like that. So this is 1 whole revolution. This right here is 1/2 of a revolution. And this here is 1/4 of a revolution. Okay. So let's see. I can go from this one as always my anchor comparison. If this is 1 whole revolution and this is 1/4, what's 1/4 of 360? That means 1/4 of 360. That gives me 90 degrees. And isn't that true? Isn't that a 90-degree angle? I have something completely horizontal and completely vertical. Okay. I can also use this as my anchor analysis. If this was half and this is 1/4, isn't this right here half of this guy? So what's half of 180? 90. Same thing over here. If this is 1/4 of that, what's 1/4 of 2 pi? That would give me 2 pi over 4, which gives me pi over 2. Or if this is my anchor comparison, and this is half of that, isn't pi radian and pi over 2 half of pi? So here in this 1/4 of a revolution analysis, this is giving me that theta is equal to 90 degrees, or theta is equal to pi over 2 radians. Okay. Let's take it one bit further. Let's go ahead and say that my angle here is half of what I just did. So just like that, this is what I'm analyzing right here. So if this is 1/4, and now I'm analyzing 1/2 of that, what's 1/2 of 1/4? Top, top, bottom, bottom, gives me 1/8 of a revolution. Okay. And so what does this mean? Let me just Here, this one whole revolution means that I look at the pizza as only one slice. 1/2 means I now have 2 slices on the pizza. 1/4 means I have 4 slices, but I'm only analyzing 1 out of the 4 slices. And 1/8 means that I cut this into 8 pieces, but I'm only looking at 1 slice out of the 8, okay? And so let's think about that. If this is my anchor point, that's going to be half of that, which gives me half of that is 45 degrees, and half of 1/2 is going to be, look at that, pi over 4. Yeah. So right here, this right here means that theta is equal to 45 degrees, or theta is equal to pi over 4 radians. I got a couple more. Because these are angles that we're going to be using a lot. Okay. Here's my unit circle. Okay. Now what happens if I cut this unit circle and I say 1/3 of a revolution? Or what if I say 1/6 of a revolution? And even I'm going to do 1/12 of a revolution. Okay. So let's see what 1/3 looks like. That means I'm going to cut my pizza into 3 equal slices. Don't pay attention to the blue. The blue is just my axis. So here's my initial ray. I'm going to cut my pizza into like a peace sign, because my peace sign is going to give me 3 equal parts. Yes? So now 1/3 of a revolution would be, that's my theta from there to there, which means I'm only analyzing from here to here, this part. And 1/6 of a revolution means that I cut these parts into 2s. So that means I have something like this. What I do? See, I should have 6 slices. Oh, I'm gonna have to draw this one again. Oh, not to worry, I got a sticker for that. So let me draw that on a nicer grid. So I'm going to look at 1/6 of a revolution. Bum, bum, bum. Problem solved. Okay. So that means I'm going to draw 3 slices up here and 3 slices down here. And I'm only going to look at that part right there. From here to here, just that part. Okay, awesome. And now the 1/12 of a revolution, let me put another grid to make it uniform. Instead of having 6 slices, I'm now gonna have 12 slices that I'm gonna look at. So that means that each quadrant is gonna have 3 slices. So right here. See it's just a sketch, but I'm just looking right now is just this little thing, which is 1/12 of a revolution. Okay. So let's recall that an entire revolution was 360 degrees, and an entire revolution is 2 pi radians. So now that I know that a third of a revolution is going to give me 120 degrees, and a third of an entire radian analysis of revolution is going to give me 2 pi over 3 rad. So I know that this theta right here is 120 degrees. Think about it. 90 plus 30 gives me 120. So theta is equal to 120 degrees, or theta is equal to 2 pi over 3 rad. You need to understand this really much, okay? Now, if I'm looking at a 6 of a revolution, that means I'm looking at 6 of a revolution. What does that give me? 36 divided by 6 gives me 6. Now, 360 divided by 6 gives me 60 degrees, or 1/6, of 2 pi radians gives me 2 pi over 6, which is really pi over 3 rad. So here, this theta here gives me theta is equal to 60 degrees, or theta is equal to pi over 3 radian. And then let's look at this one, just this little space right there. That means I'm looking at a 12th of a revolution, which is going to be 30 degrees, or a 12th of 2 pi is going to be pi over 6 radians. So there, theta is equal to 30 degrees, or pi over 6 radians. Nice little comparison here of what we're doing. Now let's talk about converting them, because it's really important that we know how to convert. So my assignment is going to ask you to draw and convert angles. So if I give you a theta, you need to convert it into the other form, and then you have to draw it. So this is going to be the assignment. It's going to say draw and convert, which means whichever format I give it to you, you have to give me the other version and then draw it up. Start with theta is equal to 50 degrees. Okay. In order for me to do this, I need to find a way to convert them, right? So let's see. I have to find a way to take, how is it that I took 360 degrees and I need to make it 2 pi rad? Okay, so we're going to do something to find that unit of that conversion unit. So let's see. I recognize there has to be a ratio because this 360 got reduced to 2. So definitely there's a ratio. I also recognize that there's a pi over here. So I know that there has to be a pi. And the pi is on top so that there's a pi over here. So 300 times something times pi gives me something times pi over here. So now I have to take this 360 and I have to make it look like a 2. So 360 divided by something has to give me 2. And that is, let's see, what's half of 360? That's 180. 360 divided by 180. Let's see what 360 divided by 180 gives us. Oh. So remember, this has to be a rad and this has to be degrees. Why? Because here, this degree is on the top, this degree is on the bottom. It cancels. This has to be a rad because that's my next one. So this right here is the unit conversion to go from degrees to radians. So to go from degrees to radians, I start with my degrees. I have to use this unit conversion, and then it's going to convert it to my radians. So right now I'm in degrees. So this is a unit conversion I have to use. So let's see if it works. Again, I have 50 degrees. I'm going to multiply that by my unit conversion, which is pi radians over 180 degrees. And I'm going to see what that gives me. Again, the degrees and degrees cancel. So I now have 50 pi over 180. Why? Because top, top, bottom, bottom. And I'm able to cancel a 10 out of here. So the zeros cancel out. I'm left with 5 pi over 18 rad. So 50 degrees is the same as 5 pi over 18 radians. Let's see what that means when I draw this out. Again, here's my unit circle. And all I'm going to do is I'm going to draw out 50 degrees. And I'm sketching this out. I recognize that this is 90 degrees, this is 180 degrees, and this is 270 degrees, and this is 0 degrees. I also recognize that this is pi radian, and then this is pi over 2 radian, and this is 3 pi over 2 radian, and this is 2 pi rad. So let's see. 45 degrees is here, just like that. So I'm just going to increase it a tiny bit because it's just a sketch. So that's my theta right there. And let's see if that makes sense. 9 pi over 18 is pi over 2, yes? So 5 pi over 18 is definitely here. So all I did is I drew it out and I converted. Okay. Let's do another one. Let's convert theta is equal to 3 pi over 4 radian. Okay. So again, I have to find a way. I need to find a conversion factor. This is the conversion factor to go from degrees to radians. Now I have to find a factor that's going to give me in the opposite manner. So let's see. If I start with 2 pi rad, I have to find something that's going to give me 360 degrees at the end. So again, this something has to multiply. I recognize that I have a pi here and I don't got a pi here, which means that this pi must be divided out. So 2 times something has to give me 360. And if you said that's 180 degrees, you're correct. So now to go from radians to degrees, here is my conversion factor right there. Notice that because I'm going this way, it's this way, and then if I return it back, it flips. There's a connection there. Okay. So I'm going to go ahead and see what I get. So I have 3 pi over 4 radians. I'm going to use my unit conversion right here. That means I have 180 degrees on top and pi rad on the bottom. Okay. Notice that my pi rad cancels. So I'm left with 180 times 3 divided by 4. So this is going to give me, let's see. Can I divide 4 out of that 180? Oops, turn it on, Daisy. 4. 45. So notice what I'm going to do. I'm going to take that 180 and I'm going to write it as 4 times 45 so that I can cancel that out. I got a 3. That 180 is really 45 times 4 over 4. So these cancel out. There's literally just my 1 left out there, my identity element of multiplication. And what's 45 times 3? 135. So 3 pi over 4 is equivalent to 135 degrees. And I'm just going to write it here too. This is 5 pi over 18 rad. So this is equal to 135 degrees. Okay. Now let's draw it. And we recognize that it's 3 45-degree angles. So let's draw it out. So 345 degrees means one of these and half of that. So right there. So this is 45, 90 plus 45 is 135. So this here is my theta. And again, remember, this is 0. This is 90. This is 180. This is 270. But it's also 0 rad, pi over 2 rad, pi rad, 3 pi over 2 rad, right? So let's see. Is that true? It's, what did we say? It was 3 pi over 4. So this is 1 pi over 4, 2 pi over 4, 3 pi over 4. Okay? That's all I want you to see, is that I'm able now to convert from degrees to radians, and I'm able to draw out that theta. I hope you enjoyed. May the 4th be with you, everybody.